Hello, my name is Lucas Andrews, and I'll be presenting the Center Buoyancy VV&T demo for Team Reacher. I am the CAD and simulation lead. Here's a look at the rest of our team with Tobias as the project manager. And we have Brian, Caleb, Sebastian, Jose, and me. So, getting a little overview of the test. The objective is to determine how well the Hero 1 aircraft is going to balance due to disturbances, takeoff, landing, any possible flight conditions in water. The driving requirements include FR8, which is Hero 1 shall have water landing capabilities. That's a big thing in like the overarching goal of our aircraft. Uh, DR 8.2, Hero 1 shall implement flotation system to prevent sinking. We obviously don't want the aircraft to sink if we're landing on water. And DR 8.2.1, Hero 1 shall have balancing flotation devices that allow for stability in water. That's just talking about our tip floats, just to make sure that like the wing's not just going straight down in the water, getting soaked. We've got a little buffer on the outside to keep everything from getting out of balance. Levels of success. So level 1 of success would be less than 15 degrees of tilt in any direction. That's assuming like our horizontal everything staying level in roll and pitch. It's okay if we spin a little bit. Um, Level 2 would be 10 degrees, and we're returning to a static state at a reasonable rate. And then level 3 would be the aircraft balances with less than 5 degrees of tilt in any direction, which would keep our propellers completely out of the water. And then a really quick return to a static state when displaced. The experimental setup changed from the pool at Carmichael to Lake Raleigh because we found out we have a little bit easier access there. The equipment needed would be the full assemble Hero 1 aircraft and a little bit of string just to keep it from floating out and a recording device. Moving on to the procedure. So the first part of the procedure is to assemble the aircraft, and because we don't want to ruin our electronic components if the test is a fail, we're going to start out with weights in place of the electronic components. Place the aircraft in the pool or water, and provide force to displace it. So I started out with right wing, left wing, then tail down and nose down. Uh, kind of increasing force as we go, adjusting ballast, which would be the weights that are in place of our battery to figure out, okay, where could we kind of move the battery around to see where this balances out better, or moving the tip floats, which is something I'll talk about later. Because you can't move the batteries too much because that also affects the CG pretty greatly. Uh, then going on from that, we're going to lift and drop and drag the rotor spars just to emulate different forms of thrust that we could see when we're trying to move the aircraft around in water or landing and such. Lift and drop the aircraft from different points to simulate like kind of an uneven landing. So just an overview of the results. We did meet the level 3 requirements, which we're going to see later on. Balancing less than 5 degrees, tilt in any direction when we're just static, and returning really quickly to the balanced position when displaced. Status, it was 100% complete on March 5th. We did do like an earlier test, but that wasn't considered satisfactory. So we went back for a second round of testing, which turned out a whole lot better with the waterproofing and everything that we improved. Um, Challenges were just scheduling a time where we could get away from other verification tests and get the aircraft down to the water because it's a big ordeal trying to get it from the lab to the water. Uh, Keeping water off the electronics is a major concern because we're not overly confident in the waterproofing of the electronics, and we would rather the aircraft's hull be waterproofed perfectly, which we think we achieved now. Um, and then waterproofing the foam joints, kind of going back to the hull. We had to improve some of the seals after the first round of water testing, where we found out that our putty was not as waterproof as we had initially thought. And here is the experimental video of us testing. You may have to turn the volume up because it's fairly quiet, but you should be able to tell what I'm doing as I go through each part of the procedure.
Well, no, I'm saying like lift up on this, lift up on the front spot. Okay. Go ahead. We're gonna do the center buoyancy test. First thing, right wing down. See how it responds. So the right wing into the water, balances out. Left wing into the water, balances out. Do it a little harder. Still fine. Still fine. Bounces out real quick. Put her tail down. Bounces out pretty quickly. Nose down. Seems pretty stable in the water. If I simulate this thing was in hover and I lift up on this and then drop it, we're going to see how it responds. Gets the tail a little wet. That's okay. That's waterproof. Same thing. Say we have too much power back here. We lift up. Pretty stable. I'm just moving it around. It doesn't seem to get water anywhere that's concerning. The tip floats seem to balance everything out pretty good so that the wings aren't getting soaked or stuck in the water. Like if I'm dragging it through and I even try to force that down, it picks it back up pretty quickly. Which is what we want. Spin it. Everything stays level. The other way, everything stays pretty level. I think that's good for my test.
So as you can see, I was pretty rough with the aircraft in the video. Definitely applying quite a bit more force than we should be experiencing, like in landing or patrolling on the water.
Well, no, I'm saying like lift up.
But kind of moving on to the results. So this is measurement just on like our static pitch angle. As you can see in the right picture, we're not moving it or anything right here. This is just a static picture of the side of our fuselage. And it's kind of hard to see, but that top line or the hypotenuse of the triangle follows a horizontal line on the piece of the side of our fuselage, and then the bottom line is going to follow the uh, water level, and then that 2 inches is the height. And what we found out is that our static pitch angle is approximately 4.76 degrees, which is less than 5, which is meeting our level 1 requirement there. And then the static roll angle, which is going to tell us like how much the wings are in the water. This was based on the just initial flotation test where we measured the tips of the propellers distance from the water. And the front right was 2 inches, front left was 1 inch. That's mostly due to just some issues we're having with the how level the wings are, even sitting on flat ground and not in water. But that being said, worst case scenario, we're still like well under the 5 degree limit we set, and it shouldn't be getting anywhere close to the water, which would be like our biggest concerns. And in hover, we wouldn't even have to worry about that because in hover, the propellers are going to be facing upward. And during patrol, we shouldn't be going fast enough to pull the propellers down into the water. So we determined that's not a concern in terms of stability and propellers hitting the water and tearing something up. Stabilization speed, as you saw in the video, it returns very, very quickly from equilibrium. Very happy with that. And we're going to improve the tip floats a little bit to even further improve that. Like I said, met all of our level 3 requirements. Very happy with this test. Yeah, great success. Few improvements can be made, mostly to the tip floats. There was an initial round, which was mostly successful in terms of stability stuff. However, we had some cracks and waterproofing stuff, so deemed it unsuccessful. Went down for another round after we re-waterproofed all the seams in our fuselage. Exterior electronics did get wet, as you could see in the video, I'm sure. kind of wanted that to happen, just test it out because it's going to happen when we land on water. And during post experiment testing, everything checked out as good. The rotors and servos were spec'd as being mostly waterproof, and as we found out, they are. Thank goodness. The water drop portion of the VV&T also demonstrated pretty good stability. I didn't show that video here, but you can see that in Tobias's VV&T, where we dropped it from I think it was 16 inches, 12 inches, and 18 inches, and even from 18 inches, we got back up to wings level very quickly, even though it sunk uh, almost down to the wings in the water at that last drop. We got back up to wings level pretty quickly, so we're not getting completely like submerged and like just sinking down into the water. It's popping right back up, stabilizing very quickly, which was a good thing to see for center of buoyancy purposes. Some further studies. If we get to get back down to the lake, goal would be to do some patrolling just to go along with some of the goals we have for our flight plan, our con ops, where we want to kind of patrol and look around for people, maybe do some communication. That would just be kind of cool to see and see how our aircraft reacts. So we'd like to do that before the first water flight, at least, to see if we can move around. Hovering over the water, one concern is the prop splash. We're not really sure how that's going to affect our electronics and stuff, and if that's going to blow water into the electronics, mess something up. Shouldn't, but we would like to see what that looks like before we just go out there and go full throttle and land on the water without like testing it out first. Yeah, so testing needs to be done. Make sure that we can also like remain balanced, remain wings level, everything looking good as we're taking off from the water and landing. Just assuming there's some resistance from the water. Not sure how those forces are going to act. Kind of need to test that before we go all out straight takeoff or land. Um, Tip float adjustment, like I mentioned earlier, we're going to make some new tip floats, make them a little bit more aerodynamic, and also uh, kind of focus them towards moving the center of buoyancy backward a little bit to adjust for that almost 5 degree pitch up that we had, which the pitch up is not the worst case scenario. It would be much worse if it were pitch down. Pitch up is actually better for us for landing and moving through water and such. So we're just going to adjust that slightly just to make sure we have just a little bit more of a cushion on the water and a little bit more aerodynamic tip floats, because the ones that we had currently are just temporary. And then the last thing is the camera. So we have not implemented the camera. We're still up for discussion on whether or not the camera is going to be focused downward where it could look underwater, or if it's just going to be a side mount or anything. However, it doesn't really affect whether or not we can fly. So if we do end up implementing the camera to be underwater, we'll just have to do another little round of testing to make sure everything around that is waterproofed. So yeah, that's all I have. If you have any questions, please email me at lgandrew@ncsu.edu. And thank you for your time.